I would like to start welcoming you all to the 18th webinar of the graduate program in physics of the Federal University of Pará in Amazonia, Brazil. I ask everyone to kindly leave the audio and video streams turned off, except for the moment you're going to speak. Questions will be allowed after the webinar, unless otherwise requested by the speaker. The questions can be asked using the chat. Today, we have the great honor to listen to Professor Matt Visser, who is a fellow of the Royal Society of New Zealand and of the American Physical Society. Among the distinctions awarded to Professor Visser, I can mention the Dan Walls Medal of the New Zealand Institute of Physics, which he received in 2013, and the Hector Medal, which is a science award given since 1912 by the Royal Society of New Zealand, which he received in the year of 2018. Professor Visser obtained his PhD from the University of California at Berkeley under the direction of Professor Mary Catherine Gaillard. Professor Visser has been working on general relativity, quantum field theory, and theoretical cosmology, with special emphasis to transversable wormholes, chronology protection, and analog spacetimes, the latter being related to his talk today. At present, Professor Matt Visser is Professor of Mathematics of the School of Mathematics and Statistics of the Victoria University of Wellington in New Zealand. Professor Visser is known worldwide for his relevant scientific contributions to gravitation and analog gravity. He has co-authored more than 250 published journal articles and the excellent textbook Lorentzian Wormholes from Einstein to Hawking, published by American Institute of Physics. But we are here today to listen to Professor Visser, so I won't take your time further with this introduction. Professor Visser, thank you again very much for having accepted our invitation. The audience is yours.
Thank you, Louise. Thank you very much for the invitation to give this seminar. What I'm planning to talk about is analog Hawking radiation and give an overall view of what is going on with Hawking radiation and how close we might possibly get to actually being able to test it experimentally. Okay, now I'm going to be talking about analog Hawking radiation rather than astrophysical Hawking radiation, because astrophysical Hawking radiation is almost a hopeless task. Whereas analog spacetimes, you use various physical analogues, typically condensed matter, to simulate the kinematic aspects of general relativity. Okay, so curved spacetimes up to including horizons and quantum fields defined on those effective analog spacetimes can be developed, but you don't get the dynamical Einstein equations. So if I try to play with these analog models, I'm only going to get half of general relativity. I'm going to get the kinematic parts. I won't get the Einstein equations. But from a theoretical perspective, those analog models are enough to let you simulate Hawking radiation, because Hawking radiation is purely kinematics. It has nothing to do actually with the dynamics of gravity. Whereas Bekenstein entropy is a more subtle thing, which is much more intrinsically tied to actually using the Einstein equations. So what I'm specifically want to focus on is that by now a number of experiments have been carried out by working with surface waves on water, photons in nonlinear optics, phonons in Bose-Einstein condensates, and these experiments probe various aspects of analog Hawking radiation, and these experiments have had a certain amount of success, which I want to actually broadcast to a wider audience. So I'm going to give you a broad overview of the experiments and the theory behind them, and discuss what you can and cannot learn from this analog of the Hawking radiation effect. Okay, so here's my rough plan, but let me give you the summary. First, analog spacetimes really are a growth industry. They are based on using effective metrics, and instead of light cones, let's call them propagation cones. Okay. There are 3 analog models that are currently amenable to experiment. Playing with surface waves on water, so ripples on the surface of water. Playing with optical pulses in fiber optics or in glass, or playing with bulk acoustics in a fluid. Unfortunately, there's a difference between what is where our theoretical understanding is best and where the experimental accessibility is best. So experimental accessibility starts with surface waves on water, optical pulses, then bulk acoustics. But when it comes to theoretical understanding, bulk acoustics is better than optics, is better than surface waves on waters. Okay. Let me give you the 1-minute summary of what I'm going to argue for. Have we experimentally seen Hawking radiation, or analog Hawking radiation? And in particle physics language, I would say yes at 3 sigma, possibly at 4 sigma, not at 5 sigma. So this is what the particle physicists would call evidence for, but not quite yet discovery. There's a couple of recent experiments done just last year. There's more in the pipeline, and I'll be talking more about that later on in the talk. Okay, where did it begin? Well, post-1980, probably the key paper to look at is in 1981, Bill Unruh wrote this paper called Experimental Black Hole Evaporation, which he published in Physical Review Letters. And that is a example of what happens when you get someone like Bill Unruh and you tell him to teach a course in fluid mechanics. Okay, he will teach the course in fluid mechanics and suddenly realize, hey, a lot of the fluid dynamical equations allow for linearized fluctuations, sound waves. Then you can start looking at effectively acoustic horizons. He called them dumb holes, which is technically correct English, but it sometimes causes people to get a little bit upset at him. But yes, certainly acoustic horizons show up in fluid mechanics. I got into this about a decade later with this article on acoustic propagation of fluids. And that, oddly enough, was based on my brother, who is an oceanographer, asking me some pointed question about sound propagation in the ocean. So based on that, I think, oh, this should be easy. No, it's not easy. Okay, but later on in 97, I wrote this up in a much longer paper and really started to push this whole business of acoustic black holes by looking at horizons, ergospheres, ergosurfaces, Hawking radiation, and so on. Historically, if you dig deeply enough, you'll find even older versions of analog models. Back in the 1920s, for instance, Gordon of the Klein-Gordon equation came up with something he called the Gordon metric, which is basically what happens in special relativity when you put a refractive index in the game, and then you have a refractive index, a fall velocity for the medium, and you can construct an effective metric that describes the propagation of light cones. Okay. As of 2011, there is a nice summary, which I will advertise even if it's my own paper, is the Analog Gravity Living Review I did with Carlos Barthelo from Spain, Stefano Liberati from Italy, and myself. This review is now 150 pages and 700 references, and if you've got any questions about these things, that review is the place to go for a detailed analysis. Okay, so let me ask, what are the generic details? What actually underlies this notion of an analog spacetime? And it's actually pretty simple. You take any physical system and split it into background plus perturbations, and treat the background as a possibly moving medium, and the perturbations can be sound waves or light waves or whatever. But as long as those perturbations have a finite propagation speed, and as long as you can actually make a clean separation between background and moving medium, then the causal structure can be summarized by propagation cones, similar to the light cones of general relativity, and that is enough to define a conformal structure. And the conformal structure really boils down to just saying, okay, I move a certain position in space, I wait a certain amount of time, I look at how the medium moves, and the light cones, and let me jump ahead now, the light cones actually, propagation cones, because I'm not making any commitment as to what it is that's happening, basically boil out at the speed of sound or the speed of ripples or the speed of light. And depending on whether or not the medium is moving subsonically, supersonically, or just at Mach 1, you will get effective horizons forming. So if I only look at the propagation cones, if I only look at the speed of the propagations, I don't actually get a metric as such. I get a conformal class of metrics, because all I can do is say, look at interval equals 0. I can define a conformal class of metrics. And if you look at that thing with it has a velocity of the medium, it has the speed of the propagation showing up, and the spatial bit tends to be completely flat. And that's simply an approximation, because most laboratory experiments are carried out in approximately flat space. But if you look at that metric, it looks very much like the ADM decomposition in general relativity. It's just that you are sitting there with a spatially flat metric. And it turns out this model is perfectly good enough to actually describe the Schwarzschild solution. You can put the Schwarzschild solution into this particular form. It's called the Panleve-Gullstrand form of Schwarzschild. Certainly, this sort of splitting into medium plus background is well defined in the Eikenau limit, and this conformal structure is good enough for many of the purposes you have, certainly good enough for Hawking radiation. Okay. First, let me define a horizon by considering two surfaces with some normal n, and demand that on the horizon, the normal velocity of the medium is equal to the propagation speed. The point is, if the normal velocity of the medium equals the propagation speed, then there is simply no way that any signal can escape from that region. Okay. Now, if I try to rewrite this in terms of the Mach number, which is just going to be defined by the velocity of the medium divided by the propagation speed, then what you really want is the Mach number multiplied by the angle between the medium flow and the normal to your surface to be 1, and call it M-perp. Okay, the normal component of the Mach number has to be 1. That defines a horizon, and you can then start to calculate things like surface gravity, because if you remember in classical general relativity, surface gravity is a conformal invariant of the metric, and the overall conformal factor just drops out of the calculation. So just working with this conformal class of metrics is good enough to let you define a surface gravity. And you just have to pick up your favorite textbook on general relativity, start calculating. And it's an easy exercise to show that the surface gravity is related to the normal derivative of the normal Mach number at the horizon. Okay, so roughly speaking, it's the normal acceleration of the medium as it crosses the horizon. And when I say more or less, the point is you actually need to look at the ratio between the medium velocity and the propagation speed, and it is that Mach number that actually drops in. And if you look carefully at this lovely formula written here, Mach number is dimensionless, gradient has units 1 over distance, so this really has distant units of speed squared over a distance, so it has the units of an acceleration. It really is the analog of a surface gravity for any one of these particular forms of conformal propagation cones, as long as there is a horizon. Okay, and the horizons actually occur when the medium goes above Mach 1. And you can copy all of the standard definitions of horizons in general relativity into this context. But now what you do, and this is what Bill Unruh did back in 1981, was to realize, go back to Stephen Hawking's original paper on black hole explosions. So this is his 2-page paper in Nature in 1974 when he announced what is now called Hawking radiation. And you stare at that paper for a while and you realize Stephen never uses the Einstein equations. They're never used, they're never needed. And so you can just copy Stephen's result into, for instance, any of these analog models, and you will get a Hawking temperature that depends now on the surface gravity divided by the speed, the propagation speed at the horizon. And when you work that out, it just depends on the gradient of the normal Mach number at the horizon times the propagation speed. And again, you can check all the dimensions there that this is precisely right. This thing is a frequency. H bar omega gives you energy. That's kBTH. Okay. And the key thing to deriving this is you need to have a quantum theory on your curved space-time. And so you need to have quantum mechanics. That's where the H bar comes in from, is you want to have a quantum field theory of either photons or phonons or whatever. You need to have a finite propagation speed just so you can define your propagation cones. And you need to have a background medium that is set up with a horizon, requiring a notion of supersonic or superluminal or super ripple speeds or whatever. And you never actually need to use the Einstein equations. Okay. On the theory side, there are 3 particular models that are most amenable to theory. There's many other analog models out there. Some of them are a lot less amenable to theory. Some of them are a lot less amenable to experimental study. So I'm going to concentrate on these 3 because between them, they cover the best theoretical laboratories and the best experimental laboratories. Okay, so I'll be talking about bulk acoustics in a fluid, optical pulses in fibers, optical pulses in glass, and surface waves on water. Okay, now the simplest analog spacetimes are the acoustic spacetimes. And the acoustic spacetimes, you can actually prove a rigorous mathematical theorem. Okay, and the theorem is this. Suppose you've got a flowing fluid, non-relativistic. I'm going to use the Euler equations plus the continuity equation. And I'm going to make technical assumptions that the fluid is barotropic, irrotational, and inviscid. Okay, barotropic is just a fancy way of saying pressure depends on density only, and we don't need to worry about extra stuff like entropy fluxes or charge fluxes or whatever. We're just going to take a very simple ideal fluid where pressure is a function of density only. Irrotational is a technical requirement. You can try to handle situations where you have vorticity. It just gets messy. And inviscid means zero viscosity. So I'm going to keep life simple by having no viscosity, so no damping. You can try to include that. That makes things messier and messier. Okay. But under those conditions where the fluid flow is barotropic, irrotational, and inviscid, then look at linearized fluctuations around some background. And the background does not even have to be time static. It can be time dependent, as long as you can make some separation of scales between the fluctuations and the time scale on which the background is evolving. You can look at those linearized fluctuations and you can describe them thanks to the irrotational condition by a velocity potential. And then when you look at the fluctuations in the velocity potential, they are described by a massless, minimally coupled scalar field propagating in a 3+1 dimensional acoustic metric, where now I can give you what the prefactor is. It just depends on the density of fluid and the speed of sound. Okay, so this, I emphasize, is a rigorous result that just drops out of linearizing the Euler equation and the continuity equation around some background. And then the thing that propagates is going to be a sound wave or a phonon if you quantize it. And I really emphasize, it really is the ordinary D'Alembert equation coming from a massless, minimally coupled scalar field. Now the metric depends algebraically on the speed of sound, the 3 velocity of the fluid, and the density of the fluid. You don't have the Einstein equations, because if you try and ask where does this metric, the specific values of V and CS and rho come from, they come from the Euler equation and the continuity equation, which are describing the background that you're linearizing around. So you do get D'Alembert equations, you do get massless, minimally coupled scalar fields, you do get a metric, but the metric is not governed by the Einstein equations. The metric is governed by the equations of fluid mechanics. And when I say fluid mechanics, this could be sound waves in air, this could be sound waves in water, this could be sound waves in any system you could think of. If I look at this metric and take its inverse, again, the inverse looks very much like the ADM decomposition for the inverse metric in the ordinary ADM formalism. I can write down the line element. I can of course calculate the Ricci tensor, and I can calculate the Einstein tensor, but I have no justification for saying Ricci tensor equals 0 or Einstein tensor equals 0. And in fact, typically, they will not be equal to 0 in this situation. So while I can certainly calculate Riemann tensor, Ricci tensor, all that stuff, you cannot then look at, you can even linearize the Ricci tensor, so the Riemann tensor, the Ricci tensor, and the Einstein tensor, but you've got no justification for setting that linearized Einstein tensor to 0. So no, you lose the Einstein equations, but you retain just about everything else. Two key things: if you move with the fluid, then the null cones simply spread out at the speed of sound. The conformal factor rho over CS drops out of specifically linearizing the Euler equations and the continuity equation. If you just were working in the, shall I say, in the the ray acoustics approximation, you couldn't detect that conformal factor. It's going to the wave acoustics approximation by actually writing down equations of motion and linearizing them that gives you that conformal factor. You can also generalize this to relativistic irrotational fluids. I just want to keep life simple, and I'm not going to go down that particular route right now, but there's places you can look that up if you want to. Now, there are physical examples where, with hindsight, you go back and you realize that people had actually seen things like this in the past. Some of you may have heard of Bondi Oil Accretion, which is what happens when interstellar fluid just drops onto some compact object. As the interstellar fluid drops, its speed increases. At some stage, the interstellar fluid is moving at the speed of sound in that fluid, and you will get an acoustic horizon. And astronomers have talked about this for decades, okay, without necessarily realizing that what they were doing was actually discussing what in Bill Unruh's language is a dumb hole, or what other people would call just an acoustic black hole. There's also a tricky thing to do with the solar wind, which is, you've all heard of the solar wind, and what you have probably not heard is that the sun is actually an acoustic white hole. The point is, the solar wind, the velocity of sound depends on the density. Somewhere near the top of the photosphere, the solar wind goes supersonic, and then remains supersonic till somewhere in the outer fringes of the solar system. So as far as acoustic perturbations are concerned, the sun is actually an acoustic white hole. And this is actually relevant for people studying the stability of the photosphere. The point is that perturbations out in the photosphere, beyond the photosphere, out in the far outside the corona, simply cannot propagate backwards because they are prevented by this acoustic white hole phenomena from propagating backwards into the sun and destabilizing the corona. The de Laval nozzle is something that engineers have worked with consistently as a way of building supersonic wind tunnels and supersonic flows in a wind tunnel situation. You basically build a nozzle to take some incoming flow of air, compress it down until the flow goes supersonic, and the physics thereafter is not what you expect. It turns out that the acoustic horizon where the flow goes supersonic is at the narrowest part of the nozzle. And once the nozzle starts opening up again, you'd normally expect, if a nozzle gets larger, the fluid to slow down, but not if there is an acoustic horizon at the narrowest point. Once you run through the relevant mathematics, you'll find that downstream from the acoustic horizon, when the nozzle opens up again, the fluid accelerates even faster. Okay, so these ideas of the de Laval nozzle in particular went into a couple of papers by Louis Garay, Anglin, Chirac, and Zoller, who built a nice theoretical model for how to try and build a supersonic flow using a Bose-Einstein condensate, and hopefully try and get around to eventually detecting Hawking radiation. These theory papers came out in the year 2000, and roughly 2018, not quite their proposal, but very similar proposals were actually finally carried out and achieved. And certainly something has been detected that looks very, very much like the notion of Hawking radiation. Another physical example comes from optics, where you use the optical Kerr effect. And the optical Kerr effect is when the refractive index depends on the presence of an imposed electric field. The only tricky thing here is you need to realize this is John Kerr, Fellow of the Royal Society from Scotland, who was doing his work in 1875. This is not Roy Kerr from New Zealand. responsible for the Kerr black hole, who did his work in 1963. So yes, it is Kerr, but it's a very different Kerr. And what the optical Kerr effect lets you do is, if you take a laser pulse with a very strong electric field, aim it down an optical fiber or through a piece of optical glass, that modifies the refractive index so that the speed of light in the center of the pulse differs from the speed of light in front of the pulse and after the pulse. And what you can then start to do is start to play some tricks. Go to the rest frame of the pulse. In the rest frame of the pulse, the medium is flowing at some constant speed v, while the propagation speed of the perturbations varies from the front of the pulse to the back of the pulse because of the fact that the electric field is changing, and so the refractive index is changing. So what you need to do is pick a suitable material with a sufficiently large Kerr constant, adjust the laser frequency and pulse amplitude to taste, arrange for optical horizons at the front of the pulse and back of the pulse, and then you just go back to copy Hawking's calculation regarding Hawking radiation, realize you've got an effective geometry, realize you're going to get, in this case, actual photons. Okay. A third model that is well adopted to explain, and the point is that these things with Bose-Einstein condensates, these things with the optical Kerr effect, and this thing I'm going to now talk about in shallow fluids, these are all well adapted to be able to play games experimentally, and all well adapted to experimental probes. Okay. For surface waves in water, you're now looking at ripples on the top of a shallow fluid. So you want the wavelengths to be much, much bigger than the depth of the fluid. And again, it's Bill Unruh with Ralph Schutzhold, came up in 2002 with a gravity wave analog of black holes. And yes, here we really do have to distinguish gravity wave from gravitational wave. Okay, most of the time in the GR community we get sloppy, but you've got to remember that gravity waves have been talked about for centuries before gravitational waves were even thought of. Gravity waves are simply what happens in a fluid when gravity is the restoring force. And the key issue here is that in a shallow fluid, the speed on which surface waves travel depends on the local acceleration due to gravity and the depth of the fluid. Now, it means in terms of, instead of looking at a Mach number, there is something equivalent for surface waves on fluids called the Froude number. And it is the ratio between the velocity at which the surface is moving divided by the velocity at which waves travel on that surface. Okay. The subtle thing with surface waves is you need to do some very, very careful and delicate approximations. The physics of the deep ocean, where the wavelength is much smaller than the depth, is very, very different. So don't try to use this analogy in the deep ocean. Everything gets very grossly modified. If you want to have a well-defined, effective 2+1 dimensional metric, because you're just looking at the surface of the fluid, you do need to work in the shallow fluid approximation. Something that often people in the relativity community do not appreciate is that fluid mechanics is much, much trickier than general relativity, especially when you're dealing with free surfaces, like the surface of water in air, or any sort of free fluid interface between two fluids. It turns out that fluid mechanics is actually much more difficult than general relativity. in general relativity, we do have, honest to God, theorems guaranteeing existence and uniqueness of solutions to the Einstein equations. In fluid mechanics, you don't have that, at least not yet, despite several centuries of work on the Euler and Navier-Stokes equations. Okay. This is not a fake photo. This is a real photo of the black hole at Monticello in California. And it is an example of, you can just see the water disappearing down in that hole. And at some stage near the edge of that hole, you do actually have the speed of the surface speed of the water exceeding the speed of ripples. The ripples can't find their way back upstream again. You do have a ripple horizon at some stage. You might wonder how on earth this thing is actually achieved. It turns out that the engineers were having fun at a water reservoir, and they built the overflow in the form of a pipe that sticks up from the bottom of the lake, and the pipe just has this lovely mouth. So this is simply the overflow to release water out of this storage dam. If you look carefully in the background here, you'll see the little red dots here. That's actually a chain of floats that are just designed to keep silly people in kayaks from getting too close to this thing, because it would be very embarrassing if you take your kayak over the top of this. Luis provided me with a similar photograph from Brazil. This is Bolhana Lake in Utinga Park in Belém. And I'm not entirely sure how much of this is exactly natural versus whether or not they actually put a weir in there. But the same sort of phenomena is happening, that at some stage you've got this water is building up, flowing over this dam-like configuration. Once the surface waves start traveling faster than the ripple speed, you've got a horizon for these ripples. You can then start doing the same calculation and try to see whether or not you can find Hawking radiation. Okay, so now let me discuss a little bit what the actual experimental situation is. Hang on just a second. Okay. Well, the experimental situation is this. The ones we can do experiments for are surface waves on water, optical pulses, and bulk acoustics in a fluid. For surface waves on water, okay, the classical limit of stimulated Hawking radiation has already been observationally detected about 9 years ago. And this is a paper, oh, guess what? It's Bill Unruh again. And this was Silke Weinfurtner, Ted Tedford, Matthew Penrose, Bill Unruh, Greg Lawrence. And back about 10 years ago, they actually got a hold of a wave tank in an engineering department in British Columbia and used the wave tank to set up a flow over a barrier. They forced that thing to go supersonic is the wrong word, super ripple speed. So the Froude number was bigger than 1 at a certain stage. And they were able to then send waves upstream towards this acoustic ripple horizon, and they saw the stuff being reflected. They saw stimulated Hawking radiation. They did see a Boltzmann factor, but because they were in the classical regime, they never really got to see the peak of the Planck spectrum. Okay. And the other thing that's difficult, in principle, you should be able to relate the Boltzmann factor, the constant of the Boltzmann factor, to the gradient of the Froude number at the place where the ripple horizon occurs. That is very difficult to verify because there's a number of technical ambiguities that come into play. Bill Unruh has very strongly argued that as soon as you see observed stimulated emission in the classical limit, that this automatically verifies the physical reality of the spontaneous quantum effect, basically on the grounds that there's enough of the relevant physics being captured that if you see the classical phenomena, you go back to some of Einstein's discussions of this A and B coefficients of emission of light from atoms, and you really get back to the spontaneous quantum effect essentially automatically. There are people who would like to see direct quantum experiments, and so that's what I'm going to be talking about now. I'll just say that in counterpoint, a number of people have discussed this classical limit of Hawking radiation, and there has been some back and forth between Germain Rousseau, Renaud Parentani, Philbin, and others. I'm still quite happy with the experiment that was carried out by Silke and Bill 10 years ago now. But I agree it is not a quantum thing. Okay. The main points of argument that are still going on is how do you include a frequency dependent for the ripple speeds in the theory? How do you handle the fact that the depth of the system is changing as you go over the barrier, so the ripple speed is changing? It's not just the velocity of this fluid that's changing, you're also seeing the depth of the fluid changing, so you need to worry about how to estimate a frequency dependent and a depth dependent Froude number. On the other hand, we do realize that the fluid mechanics have known about horizons for decades. They just didn't call them horizons. So the fluid mechanics called them wave blocking. And now I think are shifting over to the phrasing of a blocking horizon. So a blocking horizon in fluid mechanics is simply where the surface of the fluid is moving sufficiently rapidly that surface waves can't fight upstream again. And while the fluid mechanics people were not using this terminology of horizons, it's now clear from this sort of analog effect that, yes, that these really are, you can really honestly use the terminology of horizons. Okay. Optical glass. This is a way of trying to get Hawking radiation from a short laser pulse propagating through a piece of optical glass. And here are the two particular articles that came out in, again, close to 10 years ago now, 2010. The good news is it's certainly quantum, because they're certainly detecting photons. However, the bad news is there are, again, a number of issues you want to think about very hard about what is going on. And the issues I'm going to talk about are kinematics, dynamical Casimir effect, and this lovely word triboluminescence. Okay, so here is their diagram of their configuration. They have basically a rectangular piece of glass. They shine a very high intensity laser down it, and they look off to the side and they see photons coming out. Okay. Part of the problem is they're looking to the side. So your horizon should be perpendicular to the direction that the laser beam is pointing. So your horizon, I would expect to see actually Hawking photons not to be traveling parallel to the horizon, but to be traveling perpendicular to the horizon. But for technical reasons, they cannot actually carry out the experiment that way. So they are relying on looking at photons that come off at almost 90 degrees to the laser beam, so almost parallel to the horizon, which tends to make relativists a little bit queasy. The other issues are that you are actually changing the refractive index very rapidly inside that glass, so you might start worrying about a time-dependent version of the Casimir effect. And there are reasons for being suspicious. Triboluminescence is a lovely phenomena where if you take a crystal and go into a dark room and hit it with a hammer, just the fact of breaking the crystal with the hammer has the effect of breaking electronic bonds inside the crystal at a level where it's sufficient to generate visible light. Okay, so rupturing a crystal involves rupturing electronic bonds, and it can generate visible light, and this is a known effect that's been around for ages. The problem is, in this particular experiment, the laser beam is so intense that it's actually inducing rapid and irreversible phase transitions in the optical glass you are shining it through. And the reports I've heard is that you can actually hear the glass cracking as the laser beam hits it. Okay, this does indicate to me that you are running the risk that the photons you're seeing might not actually be Hawking photons, but could be coming from either dynamical Casimir effect or actually from just physically rupturing the glass. So there's a number of back and forth discussion here. The back and forth discussion boils down to, certainly it is quantum. I would even argue it is probably quantum vacuum radiation, but are we 100% sure it's Hawking radiation? Not really. Okay. Now, there have been more recent experiments, just a year or so old now, by the group of Ulf Leonhardt in the Weizmann Institute, and they now are saying that they can get stimulated emission. It's not spontaneous, but they are getting clear measurements of stimulated Hawking effect in the optical stuff. They do claim this is not a full demonstration of quantum Hawking radiation, but it does give you a quantitative experimental test of the spontaneous Hawking effect. But probably the best experiments are, well, the ones with BECs. First, let me talk about round one, which is back in 2014. These are experiments by Jeff Steinhauer at the Technion in Israel. There has been a certain amount of back and forth discussion between the people based in the Technion and the people based in the Weizmann Institute, and you'll get to see that in a few minutes. The reason Bose-Einstein condensates are good is the speed of sound in a Bose-Einstein condensate is very low. Okay, so it's millimeters per second. It's easy to induce supersonic flow in a Bose-Einstein condensate. The crudest technique is you just take a laser and use it as a stirrer, as a spatula, and get the Bose up and get the BEC moving. The other good thing about Bose-Einstein condensates are the background temperature is very low, and the background temperature is comparable to the predicted Hawking temperature. Okay, this is why, for instance, you do not want to try and use supersonic flow in water to generate the Hawking effect. First, the speed of sound in water is 1 kilometer per second. It's difficult to get fluid flows of water moving at 1 kilometer per second. You then try and run the numbers and you figure out what the temperature temperature is, and you go, wait a minute, water is at the very least got to be liquid, it's got to be at 270 Kelvin. And if your predicted Hawking temperature is very low, you're simply never going to see it. So one of the reasons people focused on Bose-Einstein condensates very early on in the game, and I think even back in the late 1990s, people were already focusing on Bose-Einstein condensates simply because the speed of sound is very low, it's easy to induce supersonic flow, and the background temperatures are very low. Okay, so here is a number of people discussing. This is the back and forth between Jeff Steinhauer at the Technion and Ulf Leonhardt at the Weizmann Institute, as they are arguing backwards and forwards about whether or not Jeff has really seen Hawking radiation. So the claims and counterclaims are actually quite tetchy. That's a good word, tetchy. Okay, so Steinhauer has reported the observation of quantum Hawking radiation. Here, the published evidence, it's consistently with theoretical bounds and statistical significance are analyzed. And so Ulf was actually pretty down on Jeff's experiment. Jeff Steinhauer's response was actually much more brutal. His comments about Ulf Leonhardt's paper was that that Ulf Leonhardt's paper misunderstood simple Fourier transforms, unnecessarily modified the experimental data, and okay. So you can see it got a little bit tetchy. But as of about a year or two ago, a really, really high quality experiment came out of the Tel Aviv group. So this is by Juan Ramon Munoz de Nova, Katrin Golubkov, Victor Kolobov, and Jeff Steinhauer. And that got published in Nature early last year as a letter. Observation of thermal Hawking radiation and temperature in an analog black hole. If you don't want the technical stuff, there's a News and Views article by Silke Weinfurtner that discusses this in a slightly less technical manner, so you can actually see some idea of what's going on. Okay, so this is all relatively recent stuff, 30th of May last year, based on papers that are just under, the experimental stuff went on the archive just under 2 years ago. It looks quite convincing. There's follow-up as of just last year, so this is now less than 1 year old, spontaneous Hawking radiation and beyond, observing the time evolution of an analog black hole, where they're actually seeing the analog black hole form and go away. So they're actually not just looking at, shall we say, steady state Hawking radiation from a effectively quasi-static black hole. They're actually looking now at time evolution. The other paper I'll mention here is this whole process now of studying analog Hawking radiation is really now a growth industry. And this article by Jacqui, Weinfurtner, and Koenig, published just quite recently this year, summarizes the next generation of analog gravity experiments and where people are going and what people are doing. And as far as I can tell, there's now something like 20-25 groups scattered around the planet, working on various different systems and working on various different experiments. So what will I conclude? Have we experimentally seen Hawking radiation? Well, yes, probably. Okay. You might remember that experimental particle physicists tend to worry about the significance of their results in terms of how many standard deviations above background you're seeing. And certainly I would say the experiments coming out of Tel Aviv and are certainly at 3 sigma, showing you that there is an effect, that it's quantum, and it's looking close enough to Hawking radiation that you really do not want to. I'm pretty convinced. I mean, I'm personally probably going to assess it as being 4 sigma. But if I'm going to be hard-hearted and say, is it 5 sigma? Is it the gold-plated standard that experimental particle physicists want? I would say not quite yet. We've certainly got evidence for, but not quite yet discovery. There's plenty of independent positive signs. There are some individual isolated measurements that have been reported at 8 sigma. Is it enough to be entirely convincing? It's pretty close. Okay, what would I still want to see? A few more replications of the current experiments, a little more time to assess the results in terms of theory and experiment, but I must say it is looking very good. If I speak as a theorist rather than an experimentalist, I would simply have to say Hawking radiation has to be there because the theoretical ingredients that go into the calculation are so fundamental. You just need an effective metric, a horizon, and some quantum field theory to describe the perturbations around that effective metric. And so unless you completely undermine the basics of quantum field theory in fact, if you don't want to use the phrase effective metric, just say quantum field theory in a background, okay? Unless you are willing to completely abandon everything we knew about quantum field theory in a experimental space-dependent, time-dependent background, then Hawking radiation pretty much has to be there. If I put on an experimental hat, or rather a theorist looking at experiment, I will say, yes, we are very, very close to being announcing discovery. Certainly we are at the stage where we have very solid evidence for. I'm just going to, shall we say, suspend disbelief for just a little bit longer until we actually get just a few more experiments and a few more slightly different systems to double check everything. And that, in fact, is about it. So at this stage, I'll say thank you. And I hope you have enjoyed all of this.
Okay, Professor Matt Visser, first of all, I would like to ask everybody to turn on their microphones for a round of applause for this excellent webinar. Thank you very much. Okay, we have the opportunity for people to make some questions. They can write down in the chat, and they can write down their questions either in English or in Portuguese, or they can simply write down, I have a question, that I will translate for them the questions in Portuguese, and I'll pass the microphone for the people that want to make questions themselves to do it, okay? Matt, I would just maybe ask you to put your presentation in the first front of your monitor. That's okay. And while people prepare for the questions, we already have some. Let me give you a kind of general idea of the audience. So although, I mean, while you speak, you have the sensation that you're talking
to no
an
one.
empty room, but then I would like to tell you that we had around almost 100 people from different places all around Brazil and abroad, from our point of view, right? So we have people from all the 5 Brazilian regions, like including the states of Pará, Amazonas, Paraíba, Rio Grande do Norte, Distrito Federal, Espírito Santo, São Paulo, Rio de Janeiro, Minas Gerais, Santa Catarina e Rio Grande do Sul. From the top north of Brazil to the bottom south of Brazil. So it's really, I mean, representative Brazilian audience. I should mention there's also our students, right? Our teachers, postdocs, and professors of the graduate program of the Pará University that I should mention: Angela Cautal, Caio Macedo, Danilo Alves, Jorge Castineiras, and Manuel Eleutério. And I'll even take the risk to mention some of the professors and teachers from all around Brazil, right? Some of them just to register their presence, like Alberto Petrov, Berta Melgar, Clóvis Maia, Emanuel Horaz, Elias Shapiro, Zé Ademir Lima, Júlio Fabres, Marcos Maia, Nádia Magalhães, Nelson Pinto Neto, Nelson Yocomizo, Odílio Aguiar, Santiago Berliafa, Tomás Pereira, and also people from abroad, like Alexander Kamenschik from Bologna University in Italy, and Geraldo Moreno from Universidade Complutense de Madrid in Spain. So having said all that, I mean, I hope people took the time to write down questions. We already have some here. So the first question is from Satish Kumar VH. He has 2 questions. Let's start by the first. Satish, do you want to make the question yourself, or do you want me to read it? Okay, then I'll read it. He wrote, we know that Hawking radiation follows the Planck black-body spectrum, maybe with gray body factors. What is the equivalent of the Planck spectrum in analog Hawking radiation?
Okay, there would still be a Planck spectrum. I mean, it'll be a Planck spectrum of phonons or a Planck spectrum of ripples. I mean, the point is, I just decided to, let's see, give the Hawking temperature here. Okay, but that Hawking temperature is just a way of summarizing the effect that there is a Planck spectrum. But the Planck spectrum, as I said, might be a Planck spectrum of phonons, it might be a Planck spectrum of ripples, it might be a Planck spectrum of, in fact, photons in these nonlinear, photons not in vacuum, but photons in a medium. So yes, there will still be a Planck spectrum. There will be gray body factors. The gray body factors could be very messy and difficult to calculate, but there will be a modulated Planck spectrum.
Okay, so thank you, Satish, for a question. Thank you, Professor Matt Visser, for your answer. Next question is from Professor Albert Petrov from University of Paraíba. Albert, do you want to make the question yourself?
Yeah. Can you hear me?
Yes, I can. I can't hear you anymore.
Albert, I will do the question for you. I will read your question, okay? If you solve your sound problems, then you just let me know. So he has written, is it well known that there can occur supersonic movement in the fluid with shock waves? It is well known that. So whether this means that superluminal movement is allowed at certain conditions?
Yes and no. Okay, first, supersonic movement in a fluid does not necessarily imply shock waves. And that was the whole point of the de Laval nozzle. The de Laval nozzle was developed by engineers to build supersonic wind tunnels, and the last thing they want to do is actually have shock waves created at the acoustic horizon before it hits their their target thing, which is to actually try and understand the dynamics of an aircraft. Does this mean that you can get superluminal motion in certain conditions? Well, yes, in a way, but also no. You don't get superluminal in vacuum. But for instance, in these optical systems that I was talking about here, the point is, in the optical glass, you have a refractive index. So the speed of light in that glass is not the speed of light in vacuum. And because of the optical Kerr effect, in fact, that refractive index is changing depending on where you are in the pulse. So yes, you can get superluminal motion in the sense of compared to the speed of light in the glass. On the other hand, that shouldn't be too surprising because that's already what happens with the Cherenkov effect, where you take a high-speed electron and throw it into some medium that has a non-zero refractive index, and that high-speed electron can easily be traveling faster than the speed of light in the medium, and it will generate photons. So yes, you can get some sort of superluminal motion, but this is not superluminal motion in the sense of fast and light in vacuum. And the other thing to probably mention is that because you've got a medium, you have a preferred rest frame. So it's superluminal motion in vacuum. You have this lovely phenomena where you can, in principle, use tachyons to talk to yourself 10 minutes ago. You can get causality violations from superluminal motion. But here, because you have a background medium, you've always got some, effectively you wind up with a metric that's always stably causal in the sense of general relativity. And so you don't wind up with causality violations. Is that more or less answering your question?
Well, I think he is not able to.
He's not able to.
Yeah, but I think you. Well, that was a very nice answer. Thank you very much. Thank you, Albert, for your question. Thank you, Matt, for your answer. Matt, people from the secretary warning me that while you project your slides, they don't see your full face there. I mean, it's up to you because then if you show your full face, then they cannot see your slides. So. I mean, it's up to you. Yeah, if you change, then it's going to be see mine. So I don't think it helps very much.
Let me see.
So we don't have too many questions. So that I think that because Satish has a second question. So I think we still have some. I mean, we have like less than 10 questions to be asked. So would you mind if I ask all of them?
No, by all means.
Okay, so let's go again to Satish. Satish normally asks the question, but maybe today he has problems with audio. So second question by Satish Kumar VH. He's in Rio de Janeiro. So you said we have to work with shallow flow. So I wonder, how does the Reynolds number affects the analog Hawking radiation?
Okay. And the answer there is I don't remember. I know I looked at that at some stage and it was not a problem, but it's too long ago. So I just, I can't give you a sensible answer there. I just don't remember at this stage. Sorry.
No problem. It's just, Matt, I would really prefer if you put your slides to the front.
The slides?
Yeah, I think it's better than me speaking. I mean, otherwise, either we can put you or other me. But that's okay. I mean, if you... Yeah, great, great. So we have a question from Mario Raya Neto. He wrote in Portuguese, and then I will translate it, right? So I will translate what he wrote, right? I hope you don't mind. So he said, Professor Matt Wormhole Master Visser, I would like to know if there is any way to create an analog for the Morris-Thorne wormhole, right? And for the warp drive Miguel Alcubierre solution. And additionally, what about in the analog models, the energy conditions and the High-Chaudhuri equation?
Okay. Okay. Let me answer a couple of those questions first. The Ray-Chaudhuri equation, again, because it's basically just kinematics, it tells you about, in general relativity, how light rays are focused by the Ricci tensor. That will actually just copy over because you don't actually need much on the Einstein equations to do it. However, the point to do with energy conditions is more subtle because you don't have the Einstein equations, you don't relate the Einstein tensor to the stress energy tensor, because you don't relate the Einstein tensor to the stress energy tensor, then the whole issue of energy conditions is just not really relevant. Okay, now you could copy over many of the modify many of the singularity theorems of general relativity, but you'd have to rephrase them not in terms of the energy conditions, but in terms of things like the Ricci convergence condition. Okay, so if you made a statement like, okay, I've got some complicated analog model, I find a metric. For that metric, I can calculate the Ricci tensor. I can then look at the null propagation cones of whatever it is that's propagating, and then I can ask if that Ricci tensor contracted with the null vectors twice, if that is always negative, then I'm going to get something like the original focusing theorems, the Ray-Chaudhuri equation, the singularity theorems. But they won't necessarily be tied to the Einstein equations. They will be tied to the fact that somehow you've calculated the Ricci tensor, somehow you've set up a configuration with a certain Ricci tensor and you will rephrase the energy conditions in terms of Ricci tensor contracted with null vector twice, Ricci tensor contracted with time-like vector twice, etc., etc. So those things you could do. Trying to do analog solutions for Morris-Thorne or the warp drive. Let's say people have tried, the results are less than entirely convincing. I mean, after all, the Morris-Thorne wormhole, if you take it seriously, the topology of the universe is non-trivial. Now, if I'm sitting here with a laboratory system, well, the laboratory has a background, laboratory time, which is going to be inherited by all of those systems. It's going to protect causality in some way. So some of the more extreme things that you can get in general relativity to do with causality violations are never going to show up in these analog models. And the Morris-Thorne wormhole, because you've got a topology change, I don't see how to get a topology change actually coming out of an analog. You can get similarities. Let me mention an example. There's something that the optics people played with hundreds of years ago, which is called the Maxwell fisheye. Okay, this is something that you can build to a certain extent in reality, but not exactly. Okay, and a Maxwell fisheye is when you have a refractive index that falls off basically as 1 over a squared plus r squared. So it falls off with a sort of Lorentzian shape. And if you have a spherically symmetric system with a refractive index that falls off like that, this so-called Maxwell fisheye, it actually, if you could continue it all the way to infinity, so your refractive index would go down to 0, it turns out you would actually have built an analog model of a Friedman-Robertson-Walker universe. Okay, because the Maxwell fisheye refocuses everything at a very large distance. And mathematically, that Maxwell fisheye with that particular fall off of the refractive index is mathematically equivalent to replacing flat space, 3 space, with a 3-dimensional hypersphere. So yes, you can kind of do that over a limited region. You won't get the entire Friedman-Robertson-Walker universe, but you could try to modify part of the Friedman-Robertson-Walker universe. People have also tried to look at how to build expanding universes, you know, with a non-trivial Hubble parameter. And there's a number of different ways. And one of them is to just take a boson on condensate and let the trap go and just let it expand into vacuum. Okay, so as it expands, the speed of sound in the condensate changes. You can get a close analog to Friedman to FLRW universes. But I think Morris-Thorne wormholes, difficult. Alcubierre warp drives, difficult. Various other interesting things, much easier to do. I should warn you, there's a whole subset of people in the condensed matter community who've recently discovered this stuff. And unfortunately, these are people who understand a lot of condensed matter, but not so much general relativity. So you'll find some pretty odd claims in the literature, like people creating so there have been claims of creating Morris-Thorne wormholes, which don't actually stack up all that well once you start looking at the technical details. Okay, I think that answers that.
Okay, thank you, Mario Neto, for your question. Thank you, Professor Matt Visser, for your answer. Now, we have a question from João Caribé. I believe he's speaking from CBPF in Rio de Janeiro. So he has written in Portuguese. I'll translate to English. Is it possible to use these analog models to understand better the information paradox, black hole information paradox?
Yes and no. In fact, I saw another question up above about the Trans-Planckian problem. So it's related to various things here. The fact that these things work in these condensed matter systems is in many ways evidence that the thing people were agonizing on about the Trans-Planckian problem is it's not really relevant. Okay, these analog systems are perfectly well working without any access to Trans-Planckian stuff. Now, the paradox of information loss, okay, here's where things get loaded. The point is, in general relativity, the horizons, if they form, are always going to be closed two surfaces. In these analog models, they don't have to be closed two surfaces. You can always, for instance, even if I've got an acoustic horizon in the laboratory, I can just walk around to the other side of the tank and, hey, I've walked around the horizon. So the point is that horizons are not, and there's easy enough to make the horizons switch off in these analog models. You just turn off the fluid flow. Okay, so horizons in this situation are nowhere near as potentially permanent as event horizons in general relativity. But what this actually does tell you is event horizons in general relativity, okay, they're great mathematics, but they're almost useless as physics. As a physicist, you really should be focusing on either trapping horizons or on apparent horizons. The problem with an event horizon is it's very precisely defined mathematically and requires you to wait till the crack of doom and backtrack from the infinite future to figure out where the boundary was of the light rays that did not manage to escape. So no one in any finite size laboratory, say a laboratory with a finite size and with a finite amount of time over which you'll collect data, nobody working under those conditions will ever, even in principle, be able to detect an event horizon. What they might be able to detect are these quasi-local ideas of apparent horizons and trapping horizons, because these are things you can decide whether or not a trapping horizon is there by making finite measurements over a finite distance scale and measurements over a finite amount of time. Now, once you're dealing with those sorts of horizons, the information problem really is not that much of a problem, because you take the horizon, you switch it off, it's gone. Okay. If you're worried about correlations between excitations on both sides of the horizon, the only reason it's particularly a problem in general relativity is because if you focus on event horizons, and if you don't focus on event horizons, it's not that big a deal. So my views on this are the analog models have really forced me to think more carefully about the distinction between event horizons and apparent trapping horizons. And my gut feeling is that that is actually quite important to finally sorting out the Transplanckian and the information problems. Okay.
Okay, so thank you very much, João Caribé, for your question. You also have put together the question by Gerardo Moreno about the Transplanckian problem. So if he wants to comment or make further questions on the subjects, just write down. Okay, Gerardo? Let me take the opportunity to mention that we have also a question in YouTube. It's about from Alan de Souza, but he got a little late, and he's asking about Hawking radiation, and he would like to know about Hawking radiation in other systems, like in analog models. Okay, so Alan, I suggest you to, so we are fortunate that Professor Matt Visser has allowed us in advance to leave this talk in our YouTube channel. So I suggest you to listen to the whole talk there, and I'm sure you're going to be very happy with that. And then we will move on to the next question. It comes from José Ademir Salles de Lima. Ademir, Professor Ademir, do you want to turn on your microphone and make the question yourself?
Yes, I will do it. Thank you, Matt, for the nice seminar. My question is very simple, actually. Any fluid, if it barotropic or not, beyond the dynamics, it also has thermodynamics. the fluid may have some temperature. And then my question is the following. Is there some theoretical relation between the temperature of the fluid and the observed temperature in the Boltzmann factor? These quantities are in some way related or not? If yes, please give me a reference.
Yeah, okay. I think the answer is no. Yes, the physical material you're working with will have some temperature. Okay, say liquid water, you're at 300 Kelvin, call it. But the actual Hawking prediction that comes out of the temperature, the Hawking temperature that comes out of the analog models really does not have anything to do with the physical temperature of the fluid. It just comes out of the surface gravity of the horizon and the perturbations. Now, the reason it becomes important is if you're trying to detect, a microkelvin of Hawking radiation in a 300 Kelvin background. No, that's simply not going to work. Okay, but in some sense, that is the same issue that we've got with general relativity black holes. I mean, if you're trying to find a general relativity black hole with a microkelvin Hawking temperature, but your background temperature from the cosmic microwave background is 3 Kelvin, you're just not going to see it. So think of what's going on basically that way. In a general relativity black hole, you get some very microscopic Hawking temperature that just depends on the physics, the quantum physics of the horizon. You're also dealing with the fact that your entire universe is sitting in a 3 Kelvin background from the cosmic microwave background. And the same sort of thing would apply with any of these analog models. Say if you're working with liquid water, you're at 300 Kelvin, okay? And you need and I do not want to have liquid water moving at 1 kilometer per second somewhere in the basement of the physics department. That is, health and safety would probably have a few things to say about that.
Okay.
So yes, there is thermodynamics of the actual material, but no, that's not what we're focused in, except as a confounding factor that makes it difficult to do the experiments.
Yeah. Thank you, Matt.
Okay, so thank you, Ademir, for your question. Thank you, Matt, for your answer. The next question comes from Cláudio de Souza. Cláudio de Souza is from Federal University of the West of Pará, in the very beautiful city of Santarém. But he's now, I believe he's speaking from Brasilia. So he wrote down 2 questions. Do you want to make it yourself, or do you want me to read it, Cláudio? So
I can make them.
Yes, please, go ahead.
Yeah, do you read me? Okay.
Yes.
Okay. Dr. Matt and Visser, is it easier to work in the shallow water region? Because if you have viscosity and things like that, it's easier to work. Né? And the second question is, what about rotating black holes? Because Zeldovich in 1971, he discovered that there is an application of the energy related to Kerr solution. So do you have something about this, study about that?
Okay.
Thank you.
Let me focus, in fact. Both of these actually are attached to each other. There are a lot of experiments carried out with so-called draining bathtub solutions, okay, which is where you basically take a shallow basin of water and you pull the plug and you let the water swirl around the plug and actually drain out. And in a situation like that, the water is moving both radially towards the plug and typically will have a certain swirling motion around the plug. So you'll have some angular velocity as well as some radial velocity. And that is actually a 2 + 1 dimensional model of, shall we say, the equator of a black hole. And one of the reasons I like those draining bathtub models is it gives you a very good model of the difference between a ergo surface and a horizon that you can actually use to teach general relativity. In a draining bathtub, the point where the speed of the water exceeds the speed of the ripples is the ergo region. And the point where the radial speed of the water exceeds the ripple speed, that is the horizon. And so you can wind up with a situation, very natural situation, with a rotating, draining bathtub where first you're going to get to a stage where you have the total speed exceed the speed of ripples. And then later on, you get a bit closer and you'll have a place where the normal component of the ripple speed exceeds the speed of water. And on the one hand, you can use this as a very nice way of explaining to graduates and undergraduates the difference between an ergo surface and a horizon. On the other hand, people have actually done these experiments, and people have, for instance, looked at vortex type fluid flows, and they have started seeing the superradiance. So Silke Weinfurtner and her group at the University of Nottingham have actually carried out experiments along these lines. And there are certainly published papers on seeing the superradiant effect that Zeldovich predicted way back when for astrophysical black holes in this analog regime. Shallow water as opposed to deep water. The point with shallow water is there you get an acoustic metric. If you have deep water, the dispersion relation between frequency and wave number is not something to form, omega is proportional to k, and so you don't get any finite propagation speed. It's not okay. The point with shallow water is the dispersion relation for surface waves in shallow water is of the form omega proportional to k. And so that means you do get finite propagation speeds. You do actually have a metric analogy. But in deep water, you don't have a metric analogy. I tried. It failed.
It says, okay. Thank you. That's very good.
Okay. So thank you, Claudio, for your question. Thank you, Professor Matt Visser, for your answer. So the next question comes from, I hope I can pronounce correctly the name, so it's Grigor Rashval. I think he's presently at the Federal University of Juiz de Fora in Minas Gerais. Grigor, do you want to make the question yourself, or do you want me to read it? So I'll read it for him. So is it possible to see a spin 2 fluctuation in any of the systems discussed? Then due to some theorems, like the Wald theorem due to Wald and others, this would imply that we will be dealing with true gravitational dynamics.
Okay. In principle, you could see spin 2 fluctuations just by, okay. Remember that what we were first doing was we were taking some object that was fluctuating on an effective background. So that rigorous mathematical theorem I showed you had to do with had to do with a velocity, the velocity potential being linearized around a curved background. Okay, so that's a spin zero fluctuation. So many of the objects we're looking at are spin zero fluctuations. Could we see a spin two fluctuation? In principle, you could try to perturb the metric itself, the effective metric. In principle, you could then try to look at the fluctuations in the Ricci tensor and the Einstein tensor. Would you want to call that a spin two fluctuation? Not really, because you can't justify saying that the linearized Einstein tensor is zero, so you cannot then justify anything like normal analysis of treating the fluctuation in the effective metric as a gravitational wave. So is it spin two? Okay, it's a fluctuation in the metric. You can get fluctuations in the effective metric, but you have no reason to believe that those fluctuations in the metric will propagate themselves as though they were spin two gravitons, and you have no reason to believe that you can get into these interacting spin two theories that give you true gravitational dynamics. The other point I'd make is those theorems require an awful lot of very, very strong additional background assumptions like perfect Lorentz invariance and so on, which you tend to be killing in all of these analog systems. For instance, if you're working in any of these analog systems, if they are condensed matter systems, eventually at short enough distance scales, you are going to see the atomic nature of matter. And so your metric is going to discretize, well, is going to break down. The whole approximation of the metric really depends on you being able to take a fluid approximation, a large distance approximation, and that's going to break down at short distances. So all of those theorems about spin two fluctuations leading to gravitational dynamics really just not going to apply in these analog models.
Okay, so thank you, Grigor, for your question. Thank you very much, Professor Matt Visser, for your answer. So we have many various acknowledgements and compliments for your excellent talk from many people. So it's indeed, I mean, an excellent talk. Thank you very much once again, Matt. There's one last question that I have identified here. It comes from Nadia Magalhães. She is attending us, I believe, from Federal University of São Paulo in Diadema. Nadia, do you want to make the question yourself, please?
Yes, I would like to.
Please go ahead.
Okay. Hi, Professor Visser. My name is Nadia Magalhães, and I would like to first thank you for this very interesting and clear webinar. My question is the following. Do you think that it would be possible to investigate galactic dynamics with analog models by considering a galaxy a very slowly rotating fluid? I suppose that if this is possible, perhaps it could help to better understand the nature of dark matter. What do you think?
I'm not sure it's going to be all that helpful. I mean, the point is that dark matter in galactic dynamics is all occurring in the weak field limit, where really it's likely to be an approximately Newtonian solution with an approximately Newtonian gravitational metric. So
Matt, your sound was a bit like it was something in front. Could you please repeat it?
Okay. I am just worried that trying to investigate.
It is a bit still, Nadia. Maybe is it the interference with your audio? So if you turn off your audio while you, yeah.
Okay, that sounded a lot better. Okay. Okay, what I was worried about is dark matter in the galaxy is really a statement about the weak field physics at large distances where the gravitational potential is small, the gravitational field is approximately Newtonian, and the metric is very, very close to flat space. So I'm not sure that actually working with a analog model is going to be that helpful, at least for that particular problem. It seems much more likely, well, no, I should probably just stop there and say I just don't think that the analog spacetimes, it might give you some very vague ideas of what to look for, but I don't think there's any real, shall we say, physically realistic model that's likely to be able to do anything to work to explain the dark matter. So sorry, I think that's just a bit too orthogonal to be a useful way of proceeding.
Okay. Thank you, Professor. Thank you.
Okay, so thank you, Nadia, for your question. Thank you very much, Professor Mattis, for your answer. So before we finish, I'll just ask everybody to turn on their microphones for a final round of applause for Professor Mattis' excellent talk that we had this afternoon in Brazil and this morning in New Zealand. Thank you very much, Professor Mattis.
Okay.